Hi everybody, in this video recording we are picking up where we left off. So if you haven't already watched the double angle identity lesson introduction, that's the first thing you should have watched. After that we moved to the second video, which was double angle identity guided examples, and we kind of progressed through a bunch of different classic examples, and we did 4 in that video, and after each example I gave you one to try on your own. And in this video we are going to do 2 more guided examples, and I will after each one assign you one to do on your own. And within so much time I have a few videos that I will keep private and hidden on YouTube, and I will share them with you to check and correct your work once you're done with the guided examples. So let's go ahead and get started. Guided example number 5. Find the exact value, and we talked about that above my head. It says it again, but exact versus approximate. When you find an exact value, no calculator. Approximate value, probably using a calculator. You're probably going to round. You're probably going to evaluate a square root or a cube root, some kind of a radical that doesn't work out nicely, which will give you an irrational number like pi or square root 2, or E, Euler's number, which is a non-repeating, non-terminating decimal, and you have to round. There's no other way to write it unless you write it as pi or E or as the radical itself. So pay attention to those words. Exact, you should not be touching your calculator. Find the exact value of cosecant2x, secant2x, and cotangent2x given this information. Secant x is -3, and again, I'm going to go over how to read this. It's pretty obvious to me when interacting with students, when I have them read me the problem and they read this as pi less than x less than 3 pi over 2 when they should have been watching these videos. Well, then you're not listening, you're not watching, you have it on mute, I don't know what you're doing. But this should be read really as x is between pi and 3 pi over 2. That's telling you where to draw the triangle, okay? So I'm just going to make sure this focus is a little bit better because I feel like it's not quite sharp. Okay, so I'm going to call this A. I'm going to call this one B and C. So when I do that work underneath or on the side, you know, we don't get confused. That's what we're looking at. So I'm going to go over here, and first thing is we don't have double angle identities. Remember, these are 2x. It's not x. You cannot use SOHCAHTOA. You can't say sine is opposite over hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent, and then boom, 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 reciprocal, cosecant hypotenuse over opposite, secant hypotenuse over adjacent, and cotangent adjacent over opposite. You can't do that. That's, I promise, it doesn't work that way. That's like saying, you know, the square root of 100 is 10. So of course the square root of 200 is 20. No, that's not true. Okay, there's procedures, and it's not going to work in that type of a variation. It's not 1-to-1 like that. So it's not a direct variation in that way. So what we'll do though, what is true, okay, we'll call this important. Important facts. Cosecant 2x equals 1 over sine 2x. Secant 2x, I really think you could really just fill them in from here, is equal to 1 over cosine 2x, and cotangent 2x is equal to, you have a few ways you can look at this, but 1 over tan 2x, and you could kind of build on that using the quotient identities in a way. So you could call it cosine 2x over sine 2x, right? And if you are really good and you remember the bonus quotient identity I gave you back a while ago, that would be C is always on top for cotangent. So cosecant 2x over secant 2x. So, and it also equals cosecant 2x over secant 2x. All right, so important, good to know. All right, we're going to end up using this information quite a bit to get through this guided example right over here. Next thing, okay, secant of x, secant, which is the reciprocal of cosine. That's what secant is. Since cosine of x is SOHCAHTOA, therefore the secant of x, again, these are just classic x. You could just do the SOHCAHTOA, right triangle trigonometry. 2x, no. Name of the section, double angle identities. So we got to use that. Equals hypotenuse over adjacent. Now, secant x equals -3. Secant x equals -3, which is the same as -3 over 1. Now, maybe that's -3 over +1. Maybe that's 3 over -1. If you remember some things that we've talked about, when we draw our reference triangle on the unit circle, the hypotenuse is never negative. So if the hypotenuse is never negative, and the hypotenuse is referring to that 3 over there, probably looking at labeling our triangle with that, okay? And that's going to be our hypotenuse over adjacent. Now, where do I draw this triangle, this reference triangle? It's not just like a geometry problem. It's going to be relative to standard position, which we draw on the xy plane. So we're told that angle x terminates between pi and 3 pi over 2. So that would be quadrant 3. So you sketch. And you really don't do this problem without drawing it. So don't try to act like oh, you know, I did it in my head. I don't really believe you. So here we go. You always connect up to the x-axis, right angle. This is reference angle x, put a little r on it, you know. This is my x-axis. This is my y-axis. Reference triangle. Hypotenuse. Adjacent. Some of you ride this struggle bus pretty hard and you still don't know which one is opposite and which one is adjacent. Adjacent is touching the angle. It is adjacent to it, it's touching it, and the opposite is completely diagonal from it, all right? Not touching it, all right? So adjacent is here. That's going to be our -1. Hypotenuse, of course, is out there. That's going to be our 3. Mystery side. How do we find that mystery side? Well, that mystery side, which I can name a variable, let's call it B, is going to be figured out using, of course, Pythagorean theorem. If it's a Pythagorean triple, of course you can reference that. Use Pythagorean theorem. A squared plus B squared equals C squared. C has to be the hypotenuse. -1 squared plus 3 squared. I just said C is the hypotenuse, and then I filled in 3. Silly me. B squared equals 3 squared. 3 squared is 9. B squared, when you square a negative, it's still positive. B squared is 8 after we had subtracted 1 from each side. And then B equals, now when you're the one who takes the square root of both sides, that's what you do here. Stop saying you square both sides. Don't say that. Cut it out. You are taking the square root. If you were to square both sides, you would get b to the 4th equals 64. Stop saying you square both sides. Square is raised to the 2nd power. Square root is the inverse operation. Use the right terminology, okay? But when you apply a square root or any even root to both sides of an equation when solving a problem, you must include the positive and negative out front. Square root of 8. Some of you may have memorized square root of 8 as a simplified radical. That's cool. Some of you know how to do it. That's good too. If you don't know, you need to find one of the videos where we go over simplifying radicals. That was lesson 1 in this class back in September. And or you have to ask for help. So plus minus root 2, 2 root 2. That's how it simplifies. No, squished over there. Based on the picture, you're going to figure out, is this going to be positive or negative 2 root 2? Look at it. Some of you still can't tell. You have no idea. This is, please listen, all right? The origin. That is the spot where the x and y axis intersect. This is understood as being on the xy plane, Cartesian coordinate plane, rectangular plane, call it what you wish. How do we go left on the x-axis in an ordered pair? To go left, the x value, or the first number in the ordered pair, is negative, hence -1. How do we go down? That would be the y value, or the second value in the ordered pair, and that would also be negative. Therefore, b equals negative 2 root 2, okay? So there we go. Everything is drawn out, labeled, and ready to go. I haven't even done the problem yet, okay? Guided example includes a bit of a lesson in it. You can't just copy it down and think that you have this done. You have to listen. Rewind it and listen again if it's not clicking. Things click after a few times. You're going to understand it. So if you have to do that, go right ahead. Now, I'm going to actually solve the problem, so I'm going to have to put a little paper over this. So I have this notebook here, and I'm just going to cover up a bit of this. So take note of this again. We're going to do part A right now, which is cosecant2x. We wrote down at the beginning that cosecant2x equals 1 over sin2x. Okay. Hopefully I could optimize this space a bit. Okay. Maximize it. So here we go. I don't need to see all of that, but I want to see that negative in front. Okay. So part A, we are trying to find the exact value of that. So we're going to find cosecant 2x. Cosecant 2x is what I start with. I'm going to just do work going down in a column vertically, and maybe I'll loop back around and go down again. But I'm just going to keep working down. I'm not going to use equal signs because I want it to look like I'm evaluating this this expression, cosecant 2x. I want you to see the evolution of it going down. Next step, I know it equals 1 over sin 2x. And I'm actually going to do part B, slightly different approach in the beginning, and you will have to choose if you like this approach better or the other approach better. I kind of like the second approach more, but I still want to show you this one. After this, that means 1 over what? You need to know your double angle identities. So I hope you at least know sin 2x. It's pretty easy to remember. And cosine 2x, even if you just memorized the first one, that's something, but it's not so bad. I promise to memorize all of them. This will be 2 sin x cosine x. Now it's x. It's not 2x anymore. These are different angles, okay? Different angles, not the same angles. So if your name is Bob, I don't know, and someone else is Billy Bob, you're not the same. Bob and Billy Bob, just because you both have Bob doesn't mean you're the same. X and 2x, they're not the same. Sine of x and cosine of x, we can find those from our beautiful picture using right triangle trigonometry, classic SOHCAHTOA. But of 2x, we needed to bust out this formula, the double angle identity, first. So coming up next, the 1 in the numerator, we'll leave it as is, over. Make sure your fraction bar is long enough for whatever it is you're doing. So I have 2. That's going to be where sin 2x goes, and that's going to be where cosine, I'm sorry, not 2x. Sine of x and cosine of x, they each go into those parentheses. So I might throw a little highlighter out here just so we know what we're doing. Now, sine of x, SOHCAHTOA, right, is opposite over hypotenuse. Cosine of x is adjacent over hypotenuse, and that's going to go here. That applies to this picture right there. Sine, again, opposite over hypotenuse. Opposite over hypotenuse. Negative 2 root 2 over 3. Cosine is adjacent over hypotenuse. adjacent over hypotenuse. And now all you have to do is simplify. That's really it. So what am I going to simplify? Okay, the 1, we're going to kind of leave it alone right now. 2 times -2 is -4 times root 2, so it's -4 root 2 times negative, so a +4 root 2. So on my new, JK, 1 over 4 root 2. Now, because people get confused, where's the main fraction bar in the problem? I'm going to make the main fraction bar over here very bold because people try to bust out some keep, change, flip, and they make a little bit of a mess. And I'm also going to, let me fix this arrow a little so it's kind of pointing more to the middle of the problem. Right now I feel like it's pointing at the bottom. So let's go like that a bit. Okay. Now, denominators. 2, listen, stop what you're doing and listen. 2 does not multiply by these two numbers. 2 is low key over a 1. So 1 times 3 times 3. That is 9. Okay. Keep, change, flip could happen now. Keep is 1. Change is changing this fraction bar operation, which is division, into multiplication. And remember, 1 is really 1 over 1. Keep, change, and then flip. 9 over 4 root 2. Obviously, multiplying by 1 is silly. And that's just our multiplicative identity. We get back the exact same thing. And I actually need to rationalize the denominator. And that was also in lesson 1, simplifying radicals. So I'm going to multiply my numerator by root 2. And I'm going to multiply my denominator by root 2. You could do 4 root 2, although I don't recommend it because it just gives you more to reduce, and that's silly. Did I just draw myself? I keep reminding you to think smarter, not harder. I've mentioned in the past, if not fairly recently, that PEMDAS is a little bit of a lie. It could be PEDMOS. You could divide before you multiply. Just be careful. But I would highly recommend it. Please. New habits. It's a good thing. Figure it out. I show it, I model it every single time. Listen to how I do things. I've been doing math for a long time. As a mentor of mine a long time ago would say, I've been doing this since God's dog was a puppy. I know what I'm telling you is a good way to do this. Just trust me. So 1 times 9 times root 2. Okay, well, that's going to get us to 9 root 2. Next. Don't reduce the root 2's. We just put them there, okay? Don't reduce them. Now slowly. 4 times root 2 times root 2 is 2. Now, maybe you just write 4 times 2. Not a bad idea. Because if these numbers are big and yicky, then, you're not going to want to multiply them. But then what happens if like that number ended up reducing with that number and you wasted your time multiplying, So always keep checking. Be efficient. So 9, does it reduce with any of these? I'm already kind of broken down. No. Finish it up. Final answer is cosecant2x equals, I'm writing as a full thought over here, 9 root 2 over 8. I'm going to put a little happy little cloud. What's his name? Bob Ross? No. Is that Bob Ross? 9 root 2 over 8, and that is it. We are done. Okay? That was just part A. But I think it's going to be easier moving forward from here. And like I said, I'm going to show you part B as opposed to part A. Part B, I'm going to show you using a slightly different strategy, which I do in a sense like better. It is literally the exact same thing. And some of you might be like, I see absolutely no difference between these two things that you just showed. And others might be like, oh yeah, I'm down with the first way more, or I'm down with the second way. Okay. All good. Just get the right answer, okay? So I'm going to model out this second approach and see if you understand, before I have to like break it down at the end and explain, see if you understand what the exact difference is. Also, if you're watching this right now, if you can put a timestamp in the comment saying when part B starts, that would be super helpful. And the same for part C and whatnot. Like any critical part in a video, if you could throw a timestamp down there, and periodically I'll go through them and put them in the description box. But I think it'll just help people jump to the part that they're looking for. All right, part B, we are finding the, always rewrite your problem, you know, like, that's not a mess. That's really quite ugly. I feel like it's always a fun challenge figuring out if I could change what I wrote into what I wanted to say without whiteout. Anyone else do that? Find secant2x, given the same information, referencing what we wrote before, it's equal to 1 over cosine 2x. So how is what I'm about to do going to be different? I'm going to straight up just find cosine. And then at the very end, I'm going to flip it. So approach number 2, find, I know I didn't really write anything out before, but you're going to see why this is different. I feel like the other way was more traditional. Find cosine 2x, then flip. But the thing is, the problem with approach number 2 is some people just forget to flip it, and then you have the wrong answer. So make sure you remember that. Okay, cosine 2x equals, we have a few identities. We could choose one of 3. I'm going to spice it up a little bit, and I'm going to use I think it's the third one, 1 minus 2 sine squared x. Okay? I think I used cosine squared minus sine squared in a different example, so, you know, I just want to change it up. And I think I did 2 cosine squared minus 1 in the on your own number 1 answer explanation, or number 2, number 3, whatever one I recorded kind of recently. So that will equal. So the other way I did vertically, and now I'm going to kind of use some equal signs as I go. Because I want to remember this is what I'm finding. Maybe at the bottom, I'm going to put a little note. If cosine, this is a good idea, this equals blank, comma, then secant 2x equals what? So we got 1 minus 2. I'm going to move a little quicker now. Sine. What does sine equal? Here's my triangle that I'm going to use. And sine is opposite over hypotenuse, negative root 2 root 2, negative 2 root 2. I keep wanting to say root 2 over 2, you know, unit circle. Negative 2 root 2 over 3. That's sine. What? I'm going to kind of show this step again. I know I've shown it already. Sine squared x means the sine of x squared. Replay that if you have to, like rewind a little bit, listen again. So now 1 minus 2, opposite over hypotenuse squared, which is negative 2 root 2 over 3. A negative squared is positive. And careful squaring these. People do weird things. Trick, I know it's rad 8. Rad 8 squared is 8. Done. That's a good trick. Write that down. But if you were squaring that, you would square the 2, get a 4, square root 2, get 2, 4 times 2, 8. The negative squares out. So 1 minus 2 parentheses, the top is 8 over, and that's 9. 2 is really a 2 over 1. You don't need a common denominator to multiply. We're going to have 1 minus 2 times 8 is, and check if you can reduce. 2 and 9, no. 8 and 1, nothing to do. But check. That's what I mean by PEMDAS being PEDMOS. 2 times 8 is 16, and 1 times 9 is 9. Then the 1 can be rewritten as 9 over 9 minus 16 over 9, which will equal negative 7 over 9. So if cosine 2x equals negative 7 over 9, then secant 2x equals negative 9 over 7. Happy little cloud. Pay attention to the little things I did to make sure that I didn't miss any answer. Otherwise, I may have messed up and forgotten to find secant. I might have just stopped when I found cosine and thought I was done. Okay, so that is right there. Then for part C, last minute right here, shortcut, we want cotangent. I'm just jumping to do this. 2x, it's going to be cosecant 2x over secant 2x. What was cosecant? It was 9 root 2 over 8. This was negative 9 over 7. Keep, change, flip. Reduce. Like I said, think smarter, not harder. Final answer, negative 7 root 2 over 8. I hope I didn't mess up in my rush. So trying to wrap this up over here. And if you understand and think you got this and you're going to recreate this on your own and do these next examples on your own, thumbs up. And if you are like, I have to watch this 100 more times to understand it, thumbs down. Here's the on your own. Press pause if you need to. Good luck, and I'll do on your own number 6 in a different video. Have a great day.